In this video, I will talk about improper integration and showing you how to deal and make it proper and wonderful. Fundamental Theorem of Calculus, Part 2, says that if f is continuous on the interval from a to b, and capital F of x is any antiderivative of f of x, then I can integrate. The key here is if f of x is a continuous function on the interval. If it's not continuous on the interval, then this gets thrown out the window. So this is what we do. We sneak up on it if we have bad points like infinity or asymptotes in the middle. Let me show you what I'm talking about. So let's say we have this 1 over x, and we want to find the area from 1 all the way out to infinity. Keep going further. To do this, we write the integral from 1 to infinity of 1 over x dx, but we can't put an infinity in the integral, so we rewrite this as a limit. We say the limit from 1 to b of 1 over x dx, which we can do. And b is going to go to infinity. Just sneak up on infinity. So this I can integrate. I get the natural log. So I've got the natural log going from 1 to b. I plug in b first, and then that goes to 0. And natural log of b is infinity. So this integral diverges. Now this makes sense, you say, Megan. Of course it makes sense, because the area under the curve, this is an infinitely long thing. Of course it's infinity. Haha. But let's try another one. Because otherwise, what's the point of doing these things? If it's always infinity, it would be moot. So let's look at this one. Same idea, 1 over x squared. I'm going from 1 to infinity. I'm going to sneak up on it again. Say the limit as b goes to infinity from 1 to b of 1 over x squared. I integrate. I get negative 1 over x. I plug in the b and the 1. 1 over b as b goes to infinity. That goes to 0, and this goes to 1, which means the limit is 1. Think about that. The limit under this curve is 1. That means it's the same area as in this purple, it's supposed to be blue, this purple square right here. That area is the same as all that area out to infinity. I think that's really cool. That's why infinity just rocks my world. This is called a convergent integral, improper integral. So if you get a number 1, it converges. If you don't get a number, or you get infinity, then it diverges. So let's look at the type of improper integrals we can have. We can go from a to infinity. We could go from negative infinity to b. I tend to put a's on the bottom and b's on the top. If that freaks you out, sorry, deal with it. I can also come from negative infinity and go to infinity. People in probability and statistics like to do that one a lot. So how do we deal with this? Well, for the first example, we say as b goes to infinity, we integrate from a to b. So we slowly sneak up on, well, I don't know how slow, we head out to infinity. Same idea over here. Is if I'm going from negative infinity to b, I say a is heading to negative infinity, then I put my nice trusty a on the bottom here. Now, if you come from negative infinity and go to infinity, we can't deal with double limits. We don't do that, so we break it up into 2. What's your favorite number in between negative and positive infinity? Mine is 0. So I look at 0. Negative infinity to 0, and then 0 to infinity. I look at each one of these separately using the previous methods, and if either one of them diverges, the whole thing diverges. So I get one that diverges, I stop. Because a lot of times you might get negative infinity here and positive infinity here, and you're going to want to say 0, but no, that's wrong. Okay. As soon as you get 1 infinity, you're done. So let's look at an example. I have the integral from 0 to infinity of 1 over the 4th root of 1 plus x. The no point is infinity, so I'm going to say the limit as in b goes to infinity of 0 to b of 1 plus x to the negative 1/4. I'm going to integrate that, so add 1 divided by what I get. I'm doing a baby substitution. The derivative of 1 plus x is just dx. So I can just do the power rule on that, since its derivative is sitting out here. So I added 1 divided by what I got. I'm going to plug in the b. Well, 1 plus b to the 3rd, as b goes to infinity, this whole thing goes to infinity. I don't care about minus 4/3. Infinity minus 4/3 is still infinity. So this guy is infinity. It diverges. Look at another one. Let's say I'm going from negative infinity to positive infinity. I'm going to split this one up into 2 different pieces. And let's do this one first. So I'm going to have the limit as a goes to negative infinity of a to 0 of 1 over 1 plus x squared. I know how to integrate that. That's arctan. And I'll plug in my 0, I'll plug in my a. Arctan of 0 is 0. As a goes to negative infinity, what is arctan of a? Let's remind ourselves of the graph of arctan. I know you know this. Here's the graph of arctan. Notice as a goes to negative infinity, my arctan graph's going to get closer and closer and closer to this horizontal asymptote at negative pi over 2. So arctan of 0 is 0. I have a negative. Arctan of a as a goes to negative infinity is a negative pi over 2. So this limit is pi over 2. Okay, so I got an answer. I got to keep going. I need to do the other one. Doing the other side, remembering what my picture looks like, I'll do the limit as b goes to infinity as the integral from 0 to b of that. Again, it's arctan. So as b goes to infinity, this becomes pi over 2, as we see from our graph, and arctan of 0 is 0. We get pi over 2. The answer, I have broken this up into two integrals. Both of them are pi. This improper integral gives me an area of pi. So the area is pi under the graph. Something I want you to think about is for what values of p is the following integral convergent? Remember, if I integrate this, I'll have x to the negative p, and I'll be taking the limit as p goes to infinity. What has to be true for p for this thing to converge? I'll leave that for you to think about. Another type of improper integrals is if you take an integral from a vertical asymptote or across an asymptote. So let's say, so C is something where it's not defined. Typically that's an asymptote, and you try to integrate right across it. Just steamroll over it. That's a no-no. So let's look at an example here. So let's look at the integral from 2 to 5 of 1 over the square root of x minus 2. Problem is, that integrand is not defined at x equals 2. We have an asymptote in our graph there. See, this is what the graph looks like. I need to sneak up on this too. So I'm going to rewrite this as the integral from a to 5, and a is approaching 2 from the positive side. Don't worry about this. It's coming from the positive side of my a. I do that because I'm OCD and I'm a mathematician. If you don't have the plus or the minus there, I'm not going to get my panties in a wad. So we have x minus 2 to the negative 1/2. As before, this is going to be a little substitution. X minus 2, the derivative is just 1, which is sitting out here. So I can treat this like a variable, one big variable, add 1, divide by what I get. A positive 1/2, dividing by 1/2, the same thing as multiplying by 2. Plug in my 5, and then plug in my a. So I have 5 minus 3. This I'll have 2 times the square root of 3, and over here I'll have a 0. So this converges. We have 2 times the square root of 3. Let's look at another example. Look at something like this. I have the integral from 0 to 3 of 1 over x minus 1. Now, the problem is I'm going from 0 to 3, and this function is not defined at 1. I have a big honking asymptote right in the middle. Here's the graph. So we have to break it up where the asymptote is. So I'm going to break this up into the integral from 0 to 1, and then the integral from 1 to 3. Pick one of them to start with. Let's do this one. Setting this up, I get b goes to, the limit as b goes to 1 from the negative side, from 0 to b. Integral of that is natural log. I want to take that from 0 to b. I plug in b. I get b minus 1 minus natural log of 0 minus 1. So this is going to be the natural log of 1, which is 0. Natural log of 0 here, well, natural log of 0 is negative infinity. So this, we're done. It diverges. You get one diverges, the whole thing diverges. For what p's will this be convergent? If I'm going from 0 to 1 of 1 over x to the p. It's undefined at 0, so you have to sneak up on the 0. You're going to get different p's. When is this going to be convergent? So remember, when you're doing improper integrals, what you need to do is sneak up on the quote-unquote bad points. I'd like to finish up this video with a theorem, the comparison theorem. If you've seen versions of this before, the squeeze theorem is the same sort of thing. If you know what's happening on the left and the right, and they meet, then you're going to squish something in the middle, and so whatever's in the middle is going to do what the left and the right are doing. This is the same idea. If I have a function on bottom and a function on top, and they're all above 0, if the top function converges, that forces the bottom function to converge. If the bottom function diverges, it's going to force the upper function to diverge. I think a visual will help make this clearer. if it's not already clear. Here's Pink Panther. He's my unknown function. Now I have a known function which converges. It's known as the cat. Clearly, the cat is going to hold Pink down, and Pink is not going anywhere. Looking at it from the other direction, Pink is still my unknown function. And suppose I have a known divergent function, which is going to push Pink up in the air. So this time, because the bottom function was divergent, Pink floats off into Never Never Land. Let's look at a math example of this. Let's say I want you to show that the integral from 0 to infinity of e to the negative x squared is convergent. The green is a graph of that. I can't integrate that, so I'm going to compare it to something that I know converges. In walks, y equals e to the negative x. I know that converges, and you're going to prove it for homework. The red is the e to the negative x. Even though it's on bottom a little bit, between 0 and 1, it's just a finite amount of area. But going from 1 to infinity, the red stays on top, and it's going to force the green to be also convergent, because I know the red is convergent. So using the comparison test, I can show that the integral from 0 to infinity of e to the negative x squared dx is convergent, because what's on top is convergent. Improper integrals was the last chunk of this section, so get ready for the test is next weekend. And that's all for now.